metals lines for conducting paths. So the holes are etched in this dielectric film, and these are then plugged with tungsten, and this dielectric field is remains over which the metal contacts are laid in the back end of the line. So this is the first contact with the source drain and the gate. So this is the first material that is implanted. And then in the back end of the lines, we deposit metal one, metal two, depending upon the complexity of of the device and the technology that we are using. It could be 5 metal line or 10 metal line layers, or even up to 15 metal layers, depending upon the number of transistors that we have to interconnect. So this is the metal one line. Here also the contacts. These are the vias. The vias are the interconnects between each metal line, and the metallization is using earlier it used to be aluminum, but as the technology node has increased, the clock speed has to be increased to reduce the RC delays. So this has now the copper damascene process is now employed in all the advanced nodes. So you can see the metal 2 and metal 3. So this process gets repeated, and finally we have a device. Finally, we have a device like this, wherein the transistors are in the active area, and then each of these transistors are connected to the or interconnected through vias to the metal lines, different metal lines, and we have a stack of metal lines before it is sent for. Then the final processing takes place, and then the wafers are then tested, and then good ties are binned out, and then and sent for packaging. So these are, I have just given you an overall high level definition of the how the process steps are involved. So as I mentioned, there are about 700 to 800 process steps in the fab, essentially involving these steps only: deposition of the metal layers, of the creating channels, creating drains, implantation process, CMP process, creating vias, and then the dielectrics and the metal lines. Now, as I mentioned, the inline metrology tool is akin to the any process, and about 1/3 of the steps are for the inline metrology. It is the film thicknesses are measured using ellipsometry or reflectometry. Thickness of gate oxide, the extinction coefficient of photoresist is a very important chemical, and the how much light it extinction coefficient means how much light it can absorb from the light source. That is also to be is measured, and then defect inspection in terms of any the type of defects. It could be particle defects, or it could be defects arising from process variations. So we have lots of defect inspection and defect review tools in the fab. So these go all along as the process is done. These inline measurements are executed concurrently. So as I mentioned, chip yield is very critical as it dictates the economics of how it is not only economics, it's also a reflection of how reliable is the process. So these chips are subject to a lot of determined functionality. So the percentage of chips that are found in a wafer which perform properly is termed as the yield. So if we have on a wafer 1,000 chips and we can get 900 chips, so 90% is the yield. And yield is very important for fabs, and this is a very most of the fabs, they guard, they don't divulge what is their yield, and because it's a reflection on the how the on the maturity of the technology, on the reliability of the technology, and the reliability of consequently the reliability of the devices. So they don't reveal the yield percentage. But as is known publicly, it is about the target yield of any good fab, of any global leader, global fab. They touch about 95 to 9 about 95% is the yield. That is a die yield. The other one is the line yield. Line yield means how many wafers are sent in and how many wafers come out of the fab. But because of the automation nowadays, line yield is almost 100%. But it is the yield that is very important for the fabs. And yield, it is not just you have to soil your hands. You have to run several lots to fine tune the process, identify the defects, and over the years you get mastery over this. And for also important is that in the design of the chips, we should incorporate the corners, how to manage the corners. Basically, managing corners means um, it refers basically to the extremes in the process variation. So the design should be able to cater to the variations in the processes that is generally encountered, because we are talking in nanometer levels, in angstrom thicknesses. So there is bound to be some variation. So a good design should take care of these process variations, and the industry standard is about 64 corners is the is generally followed in the industry nowadays. So as I earlier mentioned, the contamination could be from the dust particles or chemical contaminants or electrostatic charge. So in whenever we talk about yield, we talk about the killer defect. So in particularly in a fab, in a modern fab, the killer defect is point one defects per centimeter square. That is the stringent killer defect we are talking about. And for a killer defect, the particle size has to be about 1/5 of the feature size. For instance, if we are talking about 28 nanometer technology, then particle size has to be 1/5 of 28 nanometer. So we are talking about 5 nanometer should be the particle size. So the number of killer defects on wafers can be noted as the defect density. So defect density is in any modern fab is about zero point 0.1 per centimeter square. This is the target for any fab nowadays. And if we achieve that target, our yield will certainly be more than 90% in any fab. And accordingly, depending upon the defect density decides what type of clean rooms, what type of filtration, what type of air changes. So that dictates on the utilities and the clean rooms also. There are several models to estimate the yield. The most commonly used are the Murphy model, Poisson's model, Sheets model. So these are some of the models. I'm not going into details of, but as you these are used in the industry. So this is a typical cross section of the chip that the fabrication process that we employed from. This is the active area where the transistors or the NMOS and the gates are there, and then this is the first contact with the tungsten, and this is the metal one, and then we have the intermediate. These are called the local contacts, and these are the global contacts. So when I talk about the first the initial layers, because the transistors, the structures are very thin, so the initial contacts are very small and very thin, as these have to be interconnected with the transistors which are also smaller in size. And as we go above the metal layers, the global interconnects and they are relatively thicker and longer and widely spread. So these are the interconnects between the different metal layer, and these are called the VRs. So and these are basically the copper interconnects and the metal layers. So and then finally the passivation layer which protects the die, and then the interconnects are the then we have the packaging on these the pads are there which are connected to the outside systems. So IC progression has resulted in increased integration density, and it has improved the current driving capability. Stray capacitance has been reduced. Basically, this is stray capacitance is nothing but unintentional manifestation of electric charge in a circuit or a non-capacitive component. It can be present in any inductor or transistors or a diode. And it has also reduced in enhanced performance and speed and of course the reduction in the overall cost per chip. these are the uh, some of the benefits of IC progression that we have seen over the years. And as I mentioned, scaling challenges. There are challenges, involved in scaling. The lithography challenges, arresting of the gate leakages, control of gate, and then the introduction of new structures, new transistor structures, thin architectures. I'm coming to that in my subsequent slides. So let me talk about the lithography advancements. First of all, the lithography, uh, let me tell you that this is the most important and critical, besides other things, besides other processes, lithography. But for lithography advancements, we would not have seen the improvement in the technology nodes. Because IC fabrication is tightly related to the optical physics and where lenses and mirrors are the primary components of any lithography system. So what is resolution? Lithography is, in the lithography process, resolution, minimum feature size, minimum dimensions, minimum critical dimensions are transferred from the photomask onto the wafer. So resolution is nothing but a minimum feature dimension transferred from onto the resist film on a wafer. And if you see what is resolution formula is K1 into lambda upon Na. So the effort has always been to reduce K1 lambda, that is the wavelength, and the Na is the numerical aperture. So K1 is it's a process factor, and it is depend upon the process control, the equipment process control, and lambda is the wavelength of the source, and Na is the numerical aperture of the lens as the wafer sees it. So to increase the resolution, we have to reduce the lambda and K and the numerical aperture. So starting with the G line, photolithography systems. So G line used mercury wafer lamps as the source for the light source, and it has a the wavelength of 436 nanometer. So with this G line photolithography system, we could resolve up to 7 micron, 0.7 microns. This is 700 nanometer, zero point 0.7 microns, and then 0.7 micron, and then further it was the system got improved to I-line lithography system. So the wavelength that was used in this, basically the mercury wafer lamps are used. The wavelength is 365 nanometer, and we could go up to 350 nanometer with this 360 with this I-line lithography system. And then the so this was the light source was mercury wafer lamps, and then subsequently there was the advancement was made with the development of excimer laser technology. So this excimer laser technology was demonstrated at IBM in the year 1982. So basically, first the krypton fluoride laser, excimer laser was developed. Krypton fluoride is basically is a combination of krypton, that is the noble gas, and halogen gas. So under suitable conditions of electromagnetic or electrical stimulations, the mixture of krypton and fluoride, it emits a beam of coherent stimulated radiation, and which is the laser light in the UV range, and its wavelength is about 248 nanometers. So with this 248 nanometer, we could realize up to, say, about up to, with the resolution enhancement schemes and all that, we could realize up to 150, 100 nanometer resolution. Then came the argon fluoride laser, and argon fluoride laser again is an excimer laser. So, and it uses argon and fluorine as the mixture. Hello.
And apart from that, last group is working for data science. Our institution having big school of
Hello, hello.
Uh, so we're trying to mute him. In the meantime, you can continue.
Okay. No, I thought there was some question. That's why. Okay.
No, so we will
Hello.
take up questions at the
Okay.
end, sir.
Is it okay? Am I audible?
Yes, yes, sir.
Okay. So organ fluoride, the next excimer fluoride development was in terms of the organ fluoride laser. So the wavelength of this is 193 nanometers, and with the help of this, we could realize up to 80 nanometer feature size. Then the because of the limitation of this technology also for higher resolutions and as a resolution enhancement scheme, the usual air gap between the mask between the lens and the wafer, it was it was replaced with a liquid medium. Normally air is the medium in a dry lithography, air is the medium, but in an immersion lithography the liquid was used in place. Liquid replaced the air as the medium, and with the help of this, we could realize up to the feature size could be realized up to 36 nanometer. So why? Because the refractive index, the Na, Na is basically the sign of maximum refraction angle multiplied by refractive index of the medium through which the light passes. So all of you maybe heard about the Snell's law. That is Na is n sine phi. So, and sign of cone angle between the point of specimen and point length of the objective, and n is the refractive index. So when we change the refractive index of water is 1.44 at 193 nanometer. So accordingly, the resolution has the lambda for when we pass that argon fluoride laser through the through water as a medium, the wavelength becomes 134 nanometer. And with this, we could realize resolution up to even up to with 36 nanometer and even lower up to 28 nanometer with the help of the resolution enhancement schemes. So this is and immersion lithography continued till the new development was happened in terms of the EUV, extreme ultraviolet laser. So that was the next resolution in the revolution in the
Yes, sir.
yeah.
Actually, yeah, we are running out of time. So if you please can conclude within 5 minutes.
Okay.
Thank
So
you.
okay, I will pass to run it. So as I mentioned, there are resolution enhancement techniques, phase shift masking, off-axis elimination, source polarization. So these are all the resolution enhancement schemes that are used nowadays to realize advanced nodes 40 nanometer and below. EUV is the lithography process employed in any modern fab, which are at 40 nanometer and below technology node. So here the wavelength is 13.5 nanometer. So this is the and now the lithography, the next generation of lithography would be X-ray lithography, which can give us a wavelength of 0.7 to 1.2 nanometer. So we can have advanced nodes of 2 nanometer and below even using this X-ray lithography. So these advancements are underway. On the transistor structure advancements, so we had, I will just show that this planar FET is used up to 28 nanometer CMOS technology, and then this has been replaced with a FinFET. So this is the fin, and these are the fins, and this structure is called the FinFET. So it was introduced in the year 2011, and this is the most popular now used in the industry, because the gate is all round. You can see the gate is on the three sides of the channel, or it can be on the all the four sides of the channel. So gate has a good control on the channel. So it is reducing the leakages, the short channel effects, the leakages because of the DBIL, that drain-induced induced layer barriers, those have been improved. So these are some of the new transit structures that are nanosheets are the new structures. These are very thin structures, and we can go up to 2 nanometers. We can realize with this 2 nanometer technology nodes we can realize, and because the nanostructures and then the fork sheets, these are and the complementary field effect transistors. These are the new transistor structures that are going to be in the used in the industry. So basically, in terms of the density of the transistors, in terms of a better control of the gate over the channel and the over the speed, over the leakages, over the short channel effects. So this is the developments in that direction. So coming to the Vedanta has as you know, these are the Vedanta group is in three verticals: in the metal mining, in the energy sector, and the electronics manufacturing. They are into optical fiber, and Vedanta is also into they have acquired a company called Evan Strait. It is manufacturing LCD glasses for the substrate glass for the LCDs. This is the market for the Indian market will be growing at about 8% compared to the global market of 5%. And of this is about 54 billion will be the Indian semiconductor market in 2026. That is a projection, and of which about the mobile segment will be the major contributing factor in this market. Vedanta has made an application under the scheme of the government of India for the setting of the fabs, and our application is under active consideration, and most likely to be approved very soon, and following which the implementation of the project will be started at Dholera. So the Vedanta's vision is to set up semiconductor and display fabs in India. So it will facilitate development of electronics manufacturing cluster in the country, and the target products is all across all applications, like smartphones, TVs, ITs, consumer electronics, and these fabs will cater to both the domestic as well as the export market facility. So and in terms of the benefit that it will bring to the nation, so Vedanta is going to invest about $21 billion over the next 7 to 10 years in both these fabs. And as you know, this will have a multiplier, as any semiconductor industry or the display industry, it has a GDP multiplier effect of 20 to 23 times. There will be a direct employment of about 75,000 to 1 lakh direct employees employment for these in these fabs, indirect and direct. And of course, it will put India on a global map. In design innovation will be done in the country attuned to this fab and new products. It will help development of the new technologies and new products. And also the important thing is key capacity building. Vedanta has tied up with IITs and ISC for imparting training and for introducing specific courses for semiconductors at the BTech levels or in the master's level. Those MOUs are being with some of the IITs. We have signed the MOUs and some are under progress. So finally, it will give the Atmanirbhar Bharat, and in terms of the direct, domestic value addition, this will be about 20% to 50%. These fabs will enable such a contribution, domestic contribution. Currently, we are importing most of these devices, semiconductor devices. About 95% is being imported. So these fabs will be a great import substitution for our country, and also it will give an impetus to the local semiconductor industry. So we are planning to start the groundbreaking of the fab in the next quarter of this year, in the quarter 2 of this financial year, and the commercial production is expected from 2026 from the Q4 of 2026. So in terms of the technology, the target, the nodes that we'll be employing in this fab will be 40 nanometer, and also basically the fab will be equipped for 28 nanometer. But to start with, because this is a mature node, for 40 nanometer, we'll be getting it will be a copy exact technology for 40 nanometer, and then 28 nanometer technology will be developed. There will be some development effort needed into 28 nanometer technology, and the fab capacity will be 300 fab, and the planned capacity of this fab will be about 40,000 wafer starts per month. So that is all I had to give you about our plans and a brief on the technology advancements in the semiconductor. If there are any questions or any this thing.
Yes, sir. Thank you so much for this insightful talk. So we have
Sorry,
some
I was a bit elaborate. I have taken more time than I was allotted, but you know, it is the field is like that. We have to give more.
It's fine, sir. Actually, there are some questions for you from our participants. So
Yeah.
let me read that one by one. So our first question is, what is the progress of the industry in the field of the emerging memory technologies such as ReRAM, MRAM, PCRAM, etc.? Does Vedanta work in anything in these lines?
See, as I mentioned earlier, the memory technology is a different segment. So the nodes, the technology that are used currently for memory, realizing memory products, because you know you have to have more bits, cramped up in the circuit. So for that we have to use 14 nanometer and below technology nodes. That is the current trend. But see, because we are starting for the first time in the country, and these are very advanced nodes, so we have consciously decided to go in for a mature node, that is a 28 nanometer, which is not at the high end of the technology, but we can realize some of the memories like E-flash, E-square PROM. Those memories can be realized using 28 nanometer technology as well. Okay.
Yeah, okay, sir. So our next question is, what is the vision of Vedanta for process engineers and workforce setup in general in India?
Okay, that's a good, I mean, as I mentioned to you that for the semiconductor fab, the requirement of engineers would be of the order of about I can say about from 1,000 to 1,500. Similarly, for the display fab, another about 2,000 engineers would be needed. Okay, so we will be engaging the local engineers. We'll be taking engineers from at the graduate level, at the master's level, from institutes like IITs like yours, like IIT Guwahati and other institutes. Our teams had recently we conducted interviews at some of the IITs to induct some of the master at the engineers at the master level. So mostly it will be mix of fresh engineers, experienced engineers, and we will be training the local talent from within the country. There will be some engineers, experts from overseas, and who will be having experience, and they will be at Vedanta Fab and training the engineers from within the country. So it will be a mix of both experience as well as fresh, but Vedanta's endeavor is to engage mostly the local talent.
Thank you so much, sir. And so our next question is, what will be the process node used by Vedanta in Indian fab?
Okay. That I think I have answered in my slides. The process node will be 28 nanometer CMOS technology. That is a process node that we will be implementing in our fab. But we'll be starting with a 40 nanometer technology, because that will be a copy exact technology from an overseas fab. That will be the starting. While we are developing the 28 nanometer technology, see, the 28 nanometer technology currently that we have is an R&D grade. It has to be developed to be a production grade. So while the fab is being set up, that 28 nanometer technology would be, developed to be a full blown production grade technology. So both, to answer your question, in short, we will have 40 nanometer technology as well as 28 nanometer technology in our CMOS logic technology in our fab.
Okay, sir, thank you for your this valuable talk. Sir, we can't take, there are some more questions in our chat box for you, sir, that we can't take due to time limitations. So you can answer them in the chat box if you wish, sir.
Okay, I will do it gladly, no problem. Any
Okay.
questions? Any questions? Please feel free to ask me. Okay, so
Thank
I will sum up by saying that the fab that Vedanta is going to set up is going to be a game changer. It will be the flagship project for the whole nation. We should all be proud of this. It will bring in our aim, Vedanta's aim is to set up, is to create a Silicon Valley in the country. That is the underlying message that I want to convey to all the students community. So we are all in for a great technological challenge, great technological achievement, and we all should be proud of to become a part of this journey.
Thank you so much. Thank you.
Thank you and wish you all the best.
So moving to the next speaker of the session with Professor Saurabh Ganguly. Professor Saurabh Ganguly is currently serving as a faculty in Department of Electrical Engineering, IIT Bombay. He is also a visiting faculty at National Sciot Tung University, Taiwan. He obtained his BTech degree from IIT Kharagpur, followed by Master of Science in Software Engineering and PhD degree from University of Texas at Austin. He joined as a research scientist at Tokyo Electron Limited from February 2006 to July 2008. Then he joined as a postdoctoral fellow at University of Texas, Austin from August 2008 to July 2009. Later, he became a visiting scientist at IBM TJ Watson Research Center from May 2010 to July 2010. And he was enlisted in the IEEE Golden List in 2004. He has also been awarded with National Talent Search Scholar from 1993 to 1995 and Jagadish Bose National Science Talent Search Scholar from 1995 to 1999 and IBM IUSSTF Fellowship in Nanotechnology 2009, among many others. His research area encompasses quantum biomimetic technologies and semiconductor modeling and simulation from material to device to circuit. So today he will delivering a talk on device simulation, basic and future direction. With this, I request Professor Ganguly to kindly begin with his talk. Over to you, sir.
Thank you very much to the organizers for inviting me to give this talk and to you for introducing me. Am I audible?
Yes, sir.
Okay, so I'll share my slides. Please give me a few seconds here. Okay, are you able to see my PPT?
Yes, sir.
All right, so allow me to switch off my camera while I talk, and then I'll come back again for questions, then I'll turn it on. Okay, so I've already been introduced. Swarup Ganguly from IIT Bombay, and this will be the outline of the talk. It's about device simulation, so we'll start by looking at roadmap because that sets the tone. Then the bulk of my presentation will be about semi-classical device simulation, and then we will look at considerations beyond that in terms of materials modeling and multi-physics modeling, what those are and why we need it. and that will be the presentation. From time to time, I'll check whether I'm still audible and visible to you. Okay, so to start with, the devices roadmap. I think this is familiar to most of you, so I'll go over it very quickly. This is from very long ago, 2007. People had predicted at that time an evolution of CMOS something like this. The mainstream will be more mode, that means more and more scaling of digital CMOS. And then there were two kind of tributary streams adding on to it, more than more elements. That means known technologies being integrated, known technologies being, say, powered devices and analog and RF functions, sensors, etc. And then beyond CMOS on this side, things like resistance RAM, MRAM, and such. So this was a very old forecast. And to look at it another way, this one talks about, this is much more recent. This is from the International Roadmap for Devices and Systems. Yes? Is there a question?
No, sir. No, sir. You can continue.
Okay, very sorry. Thought I heard something. So what this one is telling you, this is a very recent, from a very recent roadmap. It talks about 3 eras of scaling, and clearly we are towards the end of the second era. The first era, which is kind of, most of you, I presume, are young people. So this is before your time, essentially, when scaling was very simple. Moore's law, I mean, implementation of Moore's law was relatively simple. You had to miniaturize the CMOS device. Well, it at least looks simple in hindsight. It wasn't perhaps so simple then. You had to miniaturize the device, so you had to manage the electric fields by doping and other device engineering. And then 2003 onwards, some new things had to be introduced. It wasn't enough to just miniaturize. I'll talk about these in some detail. And then when we look to the future, then we are looking at completely different geometries, 3-dimensional, and heterogeneous integration. That means integration of many different kinds of device functions on the same wafer. So here is what historically the device scaling was 2003 onward. So this is the beginning of the second era that we were in. So here you see that this is the PMOS. This slide is from Intel, which used to lead the industry at that time. And this is their PMOS in the 90 nanometer, which had silicon germanium in the source strain for the first time to induce mechanical strain in the channel and thereby increase mobility. So it wasn't simple miniaturization. There were other tricks you were having to do with, incorporation of new materials and strain and such. Then in 45 nanometer node, 2007 was the next very big change, which was, this is a MOSFET, metal oxide semiconductor, and forever before this, the oxide was silicon dioxide mostly with some nitridation. But this is the first time that we had a high K metal gate, so hafnium oxide kind of high permittivity dielectric, and metal gate instead of polysilicon. And then 2011 was the next big change when the device structure itself changed from this planar geometry to the 3-dimensional FinFET geometry. What you heard before me, 28 nanometer down to 28 nanometer, which is sort of between these two, it would still be the planar geometry. We would not worry about FinFETs at 28 nanometers. Okay. But let's move on and try to look at the future. So this is what the FinFET looks like, 2011 to 2022. And what we are looking at beyond that is to break up this fin and have nano sheets or nano wires horizontally, and maybe later on even vertically. And as you go on, one gets more and more creative with the geometries that you see are timed at 2030, 2034. At this point, we wouldn't be able to realize them with the process technologies that we have. But this is this is the recent past and trying to foresee the future, near and far future as well. So what does it take if I look at device technology development, right? It's rather complex business. So this is the planar MOSFET that we were familiar with until about 2010. And yeah, the 28 nanometer will still be this geometry. This is the FinFET geometry. So to design, realizing a next generation device, right? Or even, let's say a 28 nanometer device, if we want to develop that technology, um, it requires a lot of materials and process development, new materials and how to process them. That's on one side of the equation. On the other side is, after you have realized the device, you are not, fabricating a device for the sake of fabrication. You are developing this technology in order to put it into circuits and systems. So to make sure that your device is optimized for the circuit and system that you want it to be, right? Whether it's a microprocessor or a microcontroller. Earlier, there was a question about memory, right? So this comes, devices might look similar, but they will be engineered very differently depending on what system application it's going into. That is the reason why, when I was PhD student, we used to talk about an international technology roadmap for semiconductors. That was for devices. But now we have an international roadmap for devices and systems, because more and more we need to think of the device and the system application in conjunction with each other together. Okay, so that's about, the basic CMOS device, which is what we have been talking about. Let me take a minute to talk about heterogeneous integration, which is of great, increasing interest these days. So the CMOS digital is at the core of it, and there are other things we want to integrate with it as closely, as tightly as we possibly can. Heterogeneous means, diverse things coming together. So AMS here means analog and mixed signal. These two kind of rather easily go together. And then RF functions for communication. Similarly, photonics for communication, again, maybe device to device or chip to chip. Sensing functions, power management functions, and finally display. So devices for the driving the display, that is. So it is not a stretch to imagine, if we look at how our cell phone has evolved, the smartphone has evolved. It is not a stretch to imagine that the future is in heterogeneous integration, that 1 decade from now, the most compelling electronic systems that everybody will be holding in their palms, or I don't know, have wrapped around their eyes or head, will be the one which is most efficiently integrated, integration of all of these functions. So now let's, with that kind of setting the stage for what we need to do in the near and the distant future, let us get into how to design devices. I won't be talking about how to design every different type of device. We will be more or less following one path, but it's exemplary. It will illustrate how to design any kind of device. And we will start with, simple semi-classical electronic device simulation. That means what I mean by this set of terms is that I'm not immediately talking about, let's say, an optoelectronic device like a semiconductor laser, simple electronic device. And I'm talking about semi-classical. That means I'm not talking about, very quantum mechanical, resonant tunneling diode kind of device or anything like that. Again, simple device. Let us, however, start with quantum mechanics. And the reason I'm doing this is because this is the starting point for semiconductor physics or solid state physics. And very often I find that or not very often, but sometimes I find that students may not appreciate where exactly the quantum mechanics came in and where it's hidden when we do our our usual semiconductor physics. So I've tried to explain that. And then I have taken a problem for illustration. I have taken a simulation problem which does involve quantum mechanics. So quantum effects in electronic devices can be categorized into two. Covert, that means hidden, and overt, that means open. Okay. Before proceeding, let me pause for a second and check whether I'm still audible and visible at this point. Can you hear me?
Yes, Saurabh, we can hear you.
Oh, hi, Dipankar. Yeah, thank you. So
Hi,
I'll continue.
yeah.
So an example of covert quantum effect that I have shown here is the band structure, the energy versus momentum relation that I have shown here for silicon. It looks incredibly complicated, but if you have learned semiconductor devices, you know that we are able to simplify our life. We don't have to deal with this complication every day. How do we do that? From the curvature of this band, we extract an so-called effective mass, which is the mass with which electrons appear to move in the in the semiconductor crystal. And once we extract this effective mass, after that, instead of solving the Schrodinger equation of quantum mechanics, we are okay. It is okay to solve simply Newton's laws, but instead of the usual mass, just use m star, the effective mass, and all the quantum mechanics gets hidden behind it. Okay. Similarly, scattering of electrons as they move inside the crystal to give you a finite resistivity and resistance, that is also a quantum mechanical effect. But once you have calculated the mobility, you can pretend it's a classical quantity because all the quantum mechanics is hidden behind it, and you can do simple classical mechanics with the mobility. But there are some effects which you can't quite brush under the rug like that. Let me show you one example here. This is showing you on the right, the illustration here is that of an electron which is impinging on a barrier. And what you can see is that part of it is getting reflected back, and the shadow of it is getting transmitted through the other side, even though classically it cannot get over this barrier. So this process, as you know, is called quantum mechanical tunneling. There is not really an analog of it in the world of classical mechanics. And it is a problem in some situations in device physics, such as in MOSFETs, when your oxide becomes too thin and you have this kind of tunneling going on, that becomes very difficult because what is supposed to be an insulator becomes a conductor. But there are other contexts in which we are actually able to use the tunneling to our advantage, and we have come up with very useful devices that use the tunneling in this way. One example is shown here, the USB stick, which has flash memory inside it that uses tunneling for reading and writing. Okay, I'll move on and define for you now the problem which I want to solve by simulation. Okay, so here it is. It is in terms of quantum mechanics, and particularly about quantum confinement. Quantum confinement happens when I have a material of one type sandwiched between material of another type. And if this material one here is really thin, how thin? Thin on the scale of the wavelength of an electron, then I have to use quantum mechanics. I can't then brush quantum mechanics under the rug. Okay. And how do things work out then? What is different? So here is a real life. Here is this sandwich in real life. This is the FinFET, which you are holding in your hand. If you are looking at your cell phone now, it probably has a FinFET in the main processor. So if an electron is in this fin, is actually in a situation like this, in a sandwich situation like this. And then it behaves like a wave. That is what quantum mechanics is about, that waves and particles, you can't really distinguish. And so they have to be treated in this way, as I have illustrated here. If you have a string between two ends and you pull it, it vibrates in modes like this. The electron wave in the FinFET will do the same thing. So we will see how to simulate this, and we will also see what the effect of this turns out to be. I've shown you the effect here, but let me not get ahead of myself. So let us see what is needed to define to simulate this device. And this, by the way, is the main body of my talk. So I'll pause for another second here and make sure that I'm still audible and visible to you all. Can you please confirm?
Yes, sir, you are visible and audible.
Thank you. So the first step in doing a device simulation is to define the structure. So this is the 3D view of the structure, and I have shown you a top view of it. Yeah. And for many situations, it works to do a simple 2D simulation, two-dimensional simulation like this. It saves a lot in terms of computation time. Now, how do we define the structure? There are two ways to do it. I know that my talk will be followed by one from Silvaco. So you will learn about these in a much more operational and practical way. I will try to sort of guide you through the basic ideas here. So there are two ways in which the device structure can come about. One is in which you define the geometry. I say that there is a rectangle here and another rectangle here, and this rectangle is silicon, this rectangle may be something else, etc. The other way in which to obtain this device structure is by doing a process simulation. In other words, by simulating the fabrication process itself to obtain the device structure. So what I have in the next slide is a little illustration of how a process simulation works out. It is for a slightly different device structure. I apologize for that, but this is the one I had handy, so please bear with me. And this is a little bit of a digression. I just wanted to show you what happens if you want to obtain a device structure from process simulation. Okay, so the starting point is this bulk silicon, which is undoped. And the final device to be realized is this nanowire FET, which is in the future. We still don't have really nanowire FETs in production, but if you recall the forecasts that I was showing you, then this is very much part of the future. So, right, let's go through the simulation of the fabrication process. So the first step that you see is the silicon is doped, and you are able to see the doping level here. And then there is source drain epitaxy, that means growth of the source drain layers. And then you etch, that means remove material from under the nanowire, which we are trying to realize. And then you deposit a gate stack, that means gate dielectric and metal around the nanowire. And then you finally have the nanowire structure. There's no point, I mean, it won't help for us to go through too much detail here, but this is, I just wanted to illustrate for you how a process simulation yields a device structure. What I have on the top left-hand side here is a slightly different aspect, which is once I've realized the device structure, and ideally maybe it looks like this as a nanowire with a gate, what we actually simulate, again, in order to make it computationally efficient, might be one part of this. Or in here, what I'm showing you is we are simulating this in cylindrical coordinates. So we can solve this. We can essentially simulate this very three-dimensional structure using just two-dimensional, maths by using cylindrical coordinates. So all this sort of tricks come into play. But let us now get out of this little digression and come back to the main path of simulating the FinFET. So as discussed, we obtain the device structure by one of these two methods, and then we proceed to the next step, which is to define a mesh. The mesh is this thing that you are seeing here across the device. And it's basically, so here I'm showing you a two-dimensional mesh. In one dimension, the mesh is simply this kind of finite difference, which I think, again, most of you would be familiar with. The mesh is a way for you to calculate derivatives on a computer. So all of you know how to calculate dy dx given y as a function of x, but for a computer, you have to do it differently. Of course, you can input many different lookup tables with all different formulas, but in many cases, you won't know what y is as a function of x explicitly, but you can still calculate numerical derivatives by taking this kind of finite differences. And what you see is that this is an approximation. And as you know, the approximation becomes better and better the smaller these differences are. So you know that the derivative comes from taking delta x tending to 0. So what we do in the real world with a computer is that we take delta x as small as we can. So that said, I had a little question for you, which I would one likes to pose to a class in the physical mode. I will, but here I can't do that, so I'll give you the answer in a few seconds. The question is, the mesh, as you see, is denser in some regions and coarse in some other regions. Why is this? And the answer is that we can take, if y is not changing very fast or very quickly over x, then we can have a larger spacing between x2 and x1. We can take a larger delta x. But if y is changing fast with x, then x2 minus x1 has to be very small. So your mesh has to be very fine where things are changing fast. So if you have high doping somewhere, and where do you have high doping? In the source drain, you know that. So if you have high doping, you expect large electric fields. So your derivatives will be inaccurate if you take a coarse mesh there. So where things are changing fast, you have to have a fine mesh. Okay, that's the answer to this question. Okay, now let's move on and see what equations we actually need to solve. We have defined the mesh, but we have defined the mesh so that we can evaluate some derivatives. But what are those derivatives? So once we have defined the mesh, we tell that, okay, solve these equations, and we run the simulation. And when we run the simulation, then this is what happens. All of these equations get solved inside the computer, inside your simulator. Let's say Silverco. And let's take a few minutes to go over what this dense mesh of algebra is telling us. Okay. Let's start at the beginning. Or let's actually start at the right-hand side here. These equations, for the most part, are treating electron flow just like fluid flow. There is one aspect at the very bottom here, which is not like fluid flow. Otherwise, everything here is like fluid flow, which is why I have this picture. Let's start with the continuity equation. The continuity equation is essentially telling you that the number of the density of electrons inside this region. I'm of course not showing you a electronic device here. I'm showing you a lake of water, but the analogy holds very, very well. So the amount of water in this lake, how does it change? It can change because the flow of this river coming in and this river going out, the flow changes. That can change the amount of water. It can change because you have some water being added, That's generation of new water. And you can lose water by evaporation. So that is, there are these three things that can go on. And you see those three things exactly here. The density of electrons changes because there is a change in the current density, which is the flow through this river. Generation of carriers, which is this rainfall here, and recombination of electrons and holes, which is analogous to water leaving this reservoir by evaporation, recombining with the cloud. Yeah. So this is the continuity equation. And the point of this analogy is that it's very much like fluid flow. Now, how do we get the current flow? That comes from the famous drift diffusion equations. Again, these are very similar to fluid flow. There are two terms in the drift diffusion equation, to wit, the drift term and the diffusion term. The drift term is electrons flowing under an electric field, as you know. The analogy in fluid flow will be fluid flowing under pressure. And then there is diffusion, which is very familiar to all of us from everyday life. These are the two processes in drift and diffusion. So far, the continuity equations with drift diffusion current density, this is very, very much like fluid dynamics. The only thing that is different now is that because the flow is that of electrons, electrically charged particles, we also have to solve for electrostatics, the Poisson equation or Gauss's law. And we have to solve all of these equations self-consistently. That means we have to find solutions which satisfy all of these together. What I mean is that if I look at the Poisson equation here, you have to find out, given a certain charge density rho, you have to find out a voltage or a potential, so that when you substitute that potential into the drift diffusion and continuity equation, you get the same charge density that you get from electrostatics here. So the same variables satisfy all equations. That is what we mean by self-consistency. And there are very sophisticated numerical algorithms that enable that within the simulators. But there's, I mean, you could also try your hand writing simple 1D such solvers by yourself. It's not very difficult. You can do it on MATLAB or Python. Okay, so I'm kind of done with the core of my talk about device simulation. Again, I have a little question for you here, that within this framework that I have described, how do we account for things like irradiation? If I have a, let's say, a diode or a solar cell which is exposed to radiation, I have a photodiode exposed to radiation or solar cell exposed to radiation. How do I account for that? How do I account for simple things that you even learn in high school if you are reading about a diode, you know, impact ionization and, you know, tunneling, etc. So again, I would have liked to ask you these questions to your face, but given our mode, I'll just give you the answer. We account for these things through these terms, the generation and recombination terms. So we get outside of this basic simulator, the drift diffusion and continuity simulator. We calculate, you know, how much tunneling or impact ionization we expect, and then we plug that in as a generation term. We say that there will be so many more electrons that are getting generated because of a tunneling process or an impact ionization process, or, you know, because the semiconductor is irradiated. All right. Okay, so with that, I'll move on and talk about the result that we get and its interpretation. I'll take a few minutes to do that. But before that, I'll again do my pause for a few seconds and request confirmation that I'm still audible to you.
Yes, sir, you are audible.
Thank you. All right. So what I simulated here is actually pretty simple. It just solves for electrostatics. I have not actually calculated current. but it's not simple electrostatics, not just Gauss's law. I have taken quantization into effect by into account. Quantization meaning the wave nature of the electrons. So now let us look at the result that I have obtained. What I am showing you here is the hole density in this FinFET as you go from one end of the fin to the other. The blue and the black dots here are the results of a classical simulation. Classical simulation meaning there is quantum mechanics is not taken into account. Electrons are treated classically. And then this red one is actually a quantum mechanical simulation. And here you see that the density of holes goes to 0 at the end of the fin. And this you expect because remember how the string vibrates, a string which is tied at both ends, how that vibrates. Now I have a electron wave which is vibrating within this fin, and the vibrating pattern has nodes. That means 0 displacement at the two edges. That is exactly what you are seeing at the two ends. Because remember that the hole density or electron density is proportional to the square of the wave function in quantum mechanics. So the wave function has to go to 0 from the vibrating string analogy, which means the density also has to go to 0. Now this has a real, I mean, this is not just an exercise in quantum mechanics. This has a real impact on device performance. And while I have shown you a FinFET here, this kind of device, this kind of difference actually creeps in even at higher nodes, has to be taken into account even at 28 nanometers that we were hearing about. So let me sort of try to show to you what the difference is. What I'm showing you here is the centroid of the charge distribution. So let's just take half of this charge distribution because as you can see, it's symmetric on the left and the right. If I take half of it, the centroid is like the center of mass of all the holes here. And you can see that the center of mass actually shifts, right? If you look at the classical distribution, the center of mass will be, or the centroid will be much closer to the edge of the FinFET, whereas for the real quantum mechanical distribution, the center of mass will be pushed away from the edge of the FinFET towards the center. And what this means is effectively it would look like the oxide thickness on this side and this side has increased a little bit. And that will that will increase. So increase in the oxide thickness will reduce the oxide capacitance, will degrade the device performance. So there is a real impact of this. And that is, of course, why we are trying to calculate it in the first place. But this is how the device simulation works. And this is how, I mean, you have to interpret and analyze the data, the results that you get, and that will kind of usually translate into some impact on device performance and downstream into circuit performance. Okay, so with that, what I'll do is I'll now move on and look at beyond the simple stuff. So what we were looking at so far is simple stuff in the sense that we looked at semi-classical fluid flow like electron transport. We looked at, added to that, there is electrostatics.